Hi everybody, how are you today? Welcome back to the bench. So here's the problem. So we have some transistors here. Matter of fact, we have a whole bunch of transistors here and they're all the same. These ones happen to be 2N2222s. And I would like to find a way to match them. Now of course, there's a lot of different ways to match them. Some of the not super accurate ways would be to use one of these little devices that we can buy online very inexpensively. These are $10 or so online, and you can see it'll actually give you the forward gain, not a whole lot of information, and of course it only uses a little 9-volt battery. It doesn't really tell you much of anything, and you can see they all kind of read the same, and I highly doubt that they're all within one, of one another. So I don't think this is a really great way to match transistors, especially in a low noise preamp that you would be using it on. A little bit better method would be to use one of these Peak Atlas units, but they're really pricey, and they do kind of work. They actually have a 12-volt battery in them. They don't put a lot of current into the transistor, but again, it does give you a lot more information than the little cheap tester. And you can see it doesn't even match. So this one says the gain, this one over here, let's take a look. This one that we just tested was a gain of 218 on the cheap tester. Let's see what this one says. That says 190. So I'm getting different readings. And this whole thing is just, I don't really know. Now, a better way would be to use, of course, the curve tracer that you've seen on several of my videos, but those are kind of difficult to build. They're still not perfect, but they do work a lot better, and ultimately would be a commercial grade curve tracer, which can be hundreds or even thousands of dollars to even purchase a used one that's in good condition. But I really want to look for a simple way that I can match transistors and not really have to worry about the inaccuracy of all these little things. What is a cheap, simple way we can do this? Well, I'm going to show you a little trick, and hopefully this will be something that will be helpful to a lot of you, especially those of you who are just starting out or don't have a lot of money to spend on big fancy test equipment, or just don't have a lot of bench space for anything. Alright, I pulled up a little image here on the screen here, on the computer screen, and some of you may know what this is and some of you may not. This is a very, very old circuit, and it's actually a piece of test equipment from many, many years ago. And we refer to this little circuit as a Wheatstone Bridge. Now, a Wheatstone Bridge is a pretty neat piece of test equipment because it can be very, very accurate using a very small amount of components, as you can see on there. So, first thing we have is 1, 2, 3 fixed resistors. And the fourth one here, if you notice, is Rx, meaning it is a variable resistor. What do I mean by variable? Well, this is our device under test. And here's the thing. If all 4 of these resistors are exactly identical in resistance, you should have 0 volts at this center point of these 4 resistors. So in other words, the voltage here and here will be equal, and they will cancel out in the center. Now, if any one of these resistors is different from the others, then that will cause an imbalance between the resistors, and it will cause an actual error voltage to show up there. So by adjusting this resistance to match all these, we can know when this one is matched to the others by measuring 0 volts in the center. So if we go too far one direction, the voltage will be positive because one side will be higher than the other. This side may be higher than this side, P1 and P2. And if the resistance is too low, the opposite could happen. So this is a very good piece of test equipment, and this was actually something that was used many years ago to make very accurate measurements of resistances. Now, what if we could use a similar concept to test 2 transistors? In other words, what if we made one transistor be our reference transistor, and we made the other one be our device under test, DUT? Wonder if we can do that. Let's take a look at some ideas here. So I have a little circuit here, and it is very simple. And it is very simple and very inexpensive to build. Because if you look, it only has 1, 2, 3, 4, 5, 6 components. Actually 7 if we count this little switch. And let's go through it step by step. So first of all, you have your 2 transistors. And second of all, you have 2 resistors. Now, if we just ignore everything else here, ignore all of this, ignore this down here, and just look at these 1, 2, 3, 4 elements, you'll notice that we have a type of Wheatstone bridge. Now, I didn't finish drawing. There's a couple things we're going to fill in, but we just want to kind of take a look at what we're doing here first of all. Now, for an Npn resistor, and you notice I kind of drew these transistors funny because I drew the emitter as a PNP and an NPN at the same time. It's because our little circuit can be used for either a NPN or a PNP. We'll get a little more into that in a minute. So we have a couple of resistors here, and we really just kind of want to limit the current through them and kind of raise them above ground. So we're going to have these somewhere in the line of 100K. Now, I just briefly said it when we were looking at the Wheatstone Bridge, but one thing that has to happen is for everything to work, they have to be matched very, very closely. And getting a 100K resistor that's exactly perfectly on is not that easy. Those resistors are expensive and they're kind of hard to find. But what if we took a 2K potentiometer and we placed it in between these two where they would normally be connected together, and then we used the wiper of the potentiometer to adjust between these two to kind of balance them out. And that's what this little pot does. This actually, it gives us some adjustment to balance these two pots perfectly. Now, I'm going to put another little thing here. Right here is where we're going to measure with our voltmeter. This is kind of like that corner point of the Wheatstone Bridge. And if these transistors have the exact same, let's say, resistance, they conduct the same exact way, then there should be 0 volts from here to here. If one of these is imbalanced from the other, it's going to imbalance this circuit, and that imbalance is going to show up as a voltage between these 2 points here, these 2 junction points. Now, what's this up here? Well, we put a little resistor in here to give us some current limit, and also to allow us to set up a little bias voltage for our transistor. These are transistors, you know, and we have to kind of bias them. And we want to get an accurate voltage. So we have I put 2 little back-to-back diodes. Now, if you were just going to check an NPN transistor, you could just put the 1 diode in one way. If you were going to have check PNP transistors, you'd have to have the diode facing the other way. But if you take 2 diodes and you put them back to back like this, one of them will always block and one will always conduct, and either way you're going to get that 0.7 volt drop. And that's what we're actually using to bias this circuit. The bases of the 2 transistors are tied together, and they're tied to ground. And if you notice over here, we have a split rail power supply. So there's actually a plus 12 volts with reference to ground and a minus 12 volts with reference to ground. So there's minus 12 volts for an NPN anyways. There would be minus 12 volts here and plus 12 volts up here. And the resultant voltage between these two would cancel out and would equal 0. So vice versa, if we had a PNP transistor, then what we would need to do is we would need to reverse these, and we would put the negative 12 volts at this end, at the collector, and the positive 12 volts at the emitter end, and it would allow the transistor to conduct. So we put this little switch, and it is a double pole, double throw, and all it does is switch the polarity of the plus and minus 12 volts to the 2 different rails based on NPN or PNP. So between the back-to-back diodes and the switch, this allows us to easily switch between testing NPN transistors and PNP transistors. So this is kind of a transistor Wheatstone Bridge, I guess. I don't know what else you'd call it. But I've cobbled one of these together, and it actually works, and actually surprisingly works better than my other devices, with the exception of the curve tracer. It shows any little minute difference between these transistors as long as this is balanced. Now, how do we balance this? Well, I'll show you when I show you the thing, but basically all we're going to do is we're going to tie these 2 points together here and then tie them up to here, and then that's going to we're going to take our voltmeter and measure this point from here to here. And again, it makes this into a little Wheatstone Bridge, and we adjust our pot until we have 0 volts between here and here. And you'll see me do that here in a minute. Now, I did, like I said, I cobbled one of these together, and you're going to have to forgive me. Those of you who are really into neat circuitry and neat design and building, you're going to cringe. And I'm just warning you up front, if you can't take it, turn the video off now, because I didn't do a really neat job, but it works. So let's take a look at what I have. Well, here it is, the mess. And if I flip this over, it's very messy, and I'm not going to apologize for it. this was a little proof of concept, and it worked. So I thought I'd do this little video. Over here is your plus and minus 12 volt input right here, and it goes to this switch, and all the switch does is it comes in one side and then it crisscrosses. This end crisscrosses over to here, this end crisscrosses over to here, and then these two are your outputs that go into the circuit. So that allows us to swap our polarities around if we need to. We have our 3.9K, and actually I just had a 3.3K. This is not really super critical. If you want to calculate exactly how many milliamps are flowing through the transistors and everything, then these might be a little more critical. But as you're going to see, that's not going to be the point of when you're trying to match transistors. We're really not trying to measure the response curves. We're not really trying to measure the actual forward current gain. All we're trying to do is compare two transistors and see if they both perform the same or don't. If we're looking for a specific gain of a transistor, this circuit is not going to work for us. But if we're simply just trying to find two transistors that match, then this is the perfect circuit, and it's actually going to be highly accurate. You're going to find out. Now from there, we come out of our positive rail and we go through our 3.3K or 3.9K, and then we have our two back-to-back diodes and our little ground plane going around here. Sorry, I keep going off camera. Our little ground plane, and that ground jumps from here over to the bases, and you notice the bases are tied together. And I just used a couple little sockets, they're just little pin sockets that PC board mount that I had. This is all stuff I just kind of had laying around. I used a 2K pot because that's what I had, and some 100K resistors. Nothing fancy. And I had a couple of these little terminals, so to make it easier to connect the power. This is where we're going to connect our meter. And to make it easier, because transistors have different pinouts, and these are really for all the little tiny transistors. You could make a bigger model of this with jumper case, with clips or something that you could use that might be a little easier, but I just built this to be able to test the little signal transistors that you see in preamps and things, because those are really the ones that are super critical for matching, and we wanted to test. So these are 4 pins. I put the emitter on both outside pins so that no matter what order, because different transistors have different orders, so some of them are emitter, collector, base, like some of them are collector, base, emitter, some of them are emitter, base, collector. So we can always orient this in a certain way and plug it in a certain way that it will line up linearly with the pins, that's all. And both of them line up. Both your device under test and your reference device all line up. So we have emitter, emitter, collector, collector, base, base, emitter, emitter. That's all there is to the circuit. Your 2 resistors, your pot, your resistor here, and your 2 diodes. That's it. Very cheap, very inexpensive. This could be built on a breadboard. You could get really fancy if you wanted to and print and etch and print a circuit board and do a professional one, which, man, if any of you are interested in doing that, I'd be more than happy to to buy one off of you. I'm not much of a CAD person on the computer. I just don't have time to mess with those sorts of things. Always have other projects I have to do, but this would be a really cool one, I think, to make an actual circuit board for. So let's quit babbling about this and let's try it out and see how it works. Now, the very first thing you're going to want to do before you use this is you're going to want to calibrate it. And in order to calibrate it, we're going to take the outputs that go to our meter, which would be this section right here, and we're just going to plug them right into where the emitters would be. So our we're going to plug these right here where the voltmeter is. We're going to plug them right up to where the collector would be up here. So we're basically going to bypass the device. So our collector pins are right here and here, and remember they're tied together just like that. So now we're applying this voltage to these two resistors equally, because essentially they're tied together now. So we're passing this voltage straight through, bypassing, just like putting straight pieces of wire through here and here, and tying those together and applying the voltage up there. Now we're going to read on the other side of these resistors where they go into the legs of the potentiometer. And that's going to be here and here. And let me go up on the meter and I'll kind of show you, and then we're going to adjust that pot to null this out. So there it is. And if I go from here to here, we're already very, very close. And this is very touchy. I probably could even put a smaller potentiometer than a 2K to make it, because even with this, you just barely touch it, and you see how much it jumped? So it is very, very touchy, but we're looking at literally less than a millivolt, like a half of a millivolt. And you see just turning it the tiniest little bit. So really the half of a millivolt is about the closest we're going to balance these out. I can't get it too much closer, but I think if we put a smaller pot that's 10 turns, maybe a 500 ohm or a 1K ohm, we would probably be able to get it even better. So that's about as good as I can get it right now. But that's pretty close. All right, let's go back down here. So now that we've zeroed that out, and really you should only have to do that one time, I'm going to connect my meter up here. These kind of projects are fun because you experiment, and it's really neat to see things work when you're trying them out. Okay, so we connect our meter to that. And then here's the cool part. You just grab a transistor at random. And this one goes emitter base collector, I believe. Yes, emitter base collector. So we're going to put it in this orientation, emitter, base, and collector. So put this one in this way. I have to switch it to NPN mode because we're looking at an NPN transistor, I believe. Yep. So, and I need to mark these what they are. This is NPN, this is PNP up here. And the nice thing is with these high ohm resistors, even if you did hook it up backwards, unlike the curve tracer, you probably would not fry the transistor right away. So we're going to plug these two in, and we're going to look at the difference now. And you see it's just as simple as plugging those in. And if we look up at the top, we have a difference of about 5 millivolts. And it moves around a little bit as just transistors do. Let's pull this one out and watch what happens. And when we pull that out, we can see that it goes up to almost full voltage, which is our 12 volts minus the 0.7 volt drop. let's put a different transistor in. We're just leaving the first one in there all the time. We're never changing it. It's our reference transistor. And if you notice, I didn't even check to see what kind of gain it had or anything, because I don't really care. It's a reference that all the others are going to be compared to. So there's another one, and that one is about 6 millivolts. And as it warms up, it'll stabilize a little bit. This one's actually coming in a lot closer. So this one's actually has a better match than that last one. Let's put another one in. These are all pretty close. How about that one? That's a perfect match. All right, let's put another one in. Of course, I'm dropping everything here. Sorry, it's a little awkward plugging these things in. And there's another one. So you can see, as we plug these all in, and these all came out of the same batch, so they should be pretty closely matched. There's one. And that one's a little bit higher out. See that one? That one doesn't match quite as well. And now watch what happens if we get something else that's a different transistor altogether. See if we can, let's see here, hold on a second. Hopefully this is lined up right. Wow. Sorry guys. My eyesight's pretty bad lining these pins up. There we go. And you can see there, I actually have two different, I have a 2N2222 and a BC557, I think it is. And BC547, I'm sorry, which is an NPN. And you can see that's not a very good match because they have different characteristics. So I just kind of wanted to show you what, when they're really not matched, what it does. So I could sit here and go through and let's go back down here for a second. Now if I flip my switch from NPN to PNP mode, and I have some PNP transistors. Oh, let's see. And these are 2N2907s. So it's the same thing. You plug them in the same way. As long as the pinout's the same, all you have to do is flip the switch now. And we plug these in. And we go up here, and we can see very, very close match on those ones. And you can even watch them as they warm up, you can watch them kind of drift apart or get closer together. So that's another good thing, is you can leave them in there for a little bit and see how they perform after they've had power applied to them for a while. So I really like this little circuit. Think about it. When we're doing those little complementary transistors, like in the Pioneer receivers that we were looking at, in the Sansui that I did and so forth, one of the things about those is those have to be very perfectly matched. And if they're not, that can affect distortion and all kinds of things. It can cause the amp to go out of bias, all kinds of things. So it's always imperative that those are well matched. And using this method, it's pretty fail-safe. I mean, you know, it's a minimal amount of components. And so this is definitely a good thing to use, especially if you don't have a really high-end, you know, transistor tester or something like that. So I really hope you enjoyed this. I sure did. I was a little bit surprised when I tried it out that it actually worked. And yeah, I may even build a nicer version of this and start to use it. I don't know, because I'm pretty impressed with how it performs. So once again, just a little short video on this. And I thank you all for watching once again. And we have some things coming up on the bench now for the next video. Going to be getting busy here. I just thought I'd get this in here real quick. So until then, I wish you all peace, joy, happiness, and good health in your lives. I thank you all for watching. I thank you for all the wonderful, kind words and the good comments. And can't wait to do our next project. So until then, be well, take care, and we'll see you later. Bye-bye.